common components, specifically lossy passive systems and antennas. To start off, we should review the noise temperature of a resistor. We know from earlier videos that we can say resistors have a noise current variance or a noise voltage variance, as shown on this slide. I've also introduced a new schematic notation here, which is how noise sources are usually indicated in schematics. We also know from thermodynamics that the noise power is given by the noise voltage variance over 4R, and that the noise power is equal to kT times delta F. Finally, noise power is equal to kTn delta F by the way we defined the noise temperature Tn. Looking at those last two equations, it's pretty easy to see that the noise temperature of an individual resistor is just equal to the physical temperature T. If we have a lossy passive two-port network, we can try to calculate the contribution it makes to noise temperature. This schematic shows a source with a source impedance Rs driving a lossy two-port network that is terminated with a load RL. By convention, we define the noise temperature of a two-port network at the input in order to explain the noise power at the output. We know that the temperature of the source resistor and the load resistor are just T, and we're hoping to use that fact to figure out the temperature and the noise introduced by the lossy two-port, which is given by Tp. To do so, we can observe that we're assuming we're in thermal equilibrium, which means that the noise emitted by the two-port has to be equal to the noise emitted by the load. If that wasn't true, one resistor would be providing power to the other. We can calculate the noise power at the output by multiplying the input powers by the power gain. As a reminder, the power gain is like the transfer function squared, so this is consistent with our previous finding that we refer noise to different places in a circuit using the transfer function squared. Also, noise temperatures are linearly related to variance densities, so it's fine for us to add them. We're using the symbol L for power gain here to indicate that this system is actually going to have a loss, which means L is expected to be less than 1. Rearranging a little lets us calculate the temperature of the passive in terms of L and the physical temperature. Tp is equal to 1 over L minus 1 times the physical temperature. It's worth noting that this is a very powerful equation. We can use it for any lossy passive, so this works for attenuators, filters, splitters, couplers, and some mixers. If a component has an insertion loss, this equation will tell you its noise temperature. Antennas are a different case. They're passive structures, they're just pieces of metal, so you could expect them to behave like passives, but it turns out that their noise is much more dependent on the radiation that's incident on them. Various sources in the universe emit broadband radiation, and the antenna's radiation pattern will absorb that noise. So you calculate antenna temperature by integrating the radiation pattern times the received radiation temperature over spherical coordinates. In other words, you sum the total noise incident on the antenna to determine the antenna's temperature. That temperature depends a lot on what the antenna is looking at, especially if the antenna gain is high, so that its whole field of view is occupied by one radiator. For example, if you point a high gain antenna at the night sky, depending on where you look, you'll have a noise temperature of 4 to 30 Kelvin. The lower limit of 4 Kelvin in that case is the cosmic microwave background radiation, which is a famous scientific result. On the other hand, looking at Earth from space will give you a noise temperature of 290 K from the antenna. And it's just a coincidence that that 290 K number is close to room temperature. So in summary, resistor noise temperature is equal to the physical temperature. In two ports, the noise temperature is input referred, so it shows up at the input to explain the noise observed at the output. Lossy passives add noise with a temperature of Tp equals 1 over L minus 1 times T, and the antenna temperature depends on where the antenna is pointing.